Alright, let's take a look at how to create a really bare bones and basic form of 2D physics using Verlet integration. The crux of this algorithm lies in its speed. It's not necessarily the most accurate algorithm out there. There are other algorithms that maybe in the future we'll take a look at those. This is known for its speed. It uses the current position and the old position of a point to move it. So the point essentially follows inertia. The first thing we will do is create a point. Second thing we will look at is creating sticks. Sticks is nothing but just a class that has two references to the 2 points that it is connected to. Now the system is basically done here, but we will expand on it a little more and add a feature to add points and add sticks. We'll make some cool shapes with it and conclude this video there. First thing first, let's make a directory for our files to stay in. I already have all the integration taken here, so I'll name it Verlet integration tutorial. We'll make a new text file, name it main.py. We'll open this in VS Code. So before even starting to code, I suppose I should explain this, how we are going to achieve. So suppose this is our ball and this is the current position. Now this will have access. This is going to be a class in our code, so this will have access to its old position, which let's just say is here. Next frame, we will calculate this difference and just add this difference to the current position, and this will give us our future position to move in. And then we'll just set the old position to the previous current position and the current position to be this future position here. Let's get coding. We will use Pygame for rendering all that stuff. Import sys pygame.init, initialize pygame. We'll make our screen using pygame.display.setMode. Set mode. Let's make a 720p screen. We'll make a while true loop for event in pygame.event.get. If event.type equal pygame.width, pygame.width, sys.exit. We'll fill the screen with a nice dark gray color. We will update the screen. So the difference between this and .flip and .update is .update can update sections of the screen. So say if you only wanted to update half of the screen, you can do that, but flip and updates the entire screen. So I prefer using that. Let's try running it. Okay, here's our window, closes nicely. So let's make our two other crucial files, which is point.py and stick.py. These will both use Pygame for rendering and have a class point and the class is stick. So what will a point need? It will need its position right now. So this will be a tuple. It will need its old position, which will also be a tuple. We can we can define radius, but I guess we can do that later. So self.position x equal position is 0. Same with y, and then same with old position, old position dot old position x, old position y. Let's make a update method which will return nothing. Let's also specify this init function is going to return nothing. I like to be specific. So, like we saw, we will add this difference between the current position and the old position. So let's make a variable, velocity x. It will be a float, and this will be self.position x minus self.old position x, and same with velocity y, but just in the y. And then we will just self.position x plus equals velocity x, self.position y plus equals velocity y, and we'll set the old position to be self.position.x. We should do this before updating the position, because then it will be just duplicate of the position. So let's also really quickly make a render function for the points. This will take a surface to render on. We'll also specify pygame.surface type. This will return nothing. Pygame.draw.circle on our surface in color white at self.position. Oh, we need parentheses. Self.position x, self.position y, and we'll give it a radius of 5. So if we say that points, let's make an array, and we will also, we need to import from point, import point, and from stick, import stick. I will also increase the font size. I'm just now realizing. Yeah, in the points array, we will just make a singular point at 100, needs to be in a tuple. Old position, let's just say 95, and we will just say for point in points, point dot update, and point dot render. We should see screen. Why is it not going? What did he screw up? Oh, this should be right. Oh, old position. We screwed up in the init function. So yeah, it's still off the screen. Let me make this something small, like 99.99. We should see it going diagonal. What's happening? Okay. Here. Well, so we have our basic movement working, and so how do we implement, say, gravity? So what we can do is, when we are adding this difference, we can modify it a bit. Let's just say we add some arbitrary amount of gravity as well, so this point doesn't end up here, but ends up here instead. Or we can also add some friction, so it doesn't end up here, but ends up here instead. It loses some of its energy each frame. So let's do that. This update function will take gravity, it will take friction, and when we are multiplying this, actually, self.position.y plus gravity. So gravity is fixed, and here we can just multiply it friction. So in our project, let's just say gravity is 1 pixel and friction is 0.99, so it loses 1% of its energy each frame. Uh, oh, gravity, friction. There we go. Okay, so gravity is working fine. And what if gravity is zero, but we lose 90% of our energy each frame? So yeah, it eventually comes to a stop. So let's keep gravity at 0.1, friction we'll keep just at 1. We won't use friction for now. Okay, we have our stuff sorted out. Now let's see how we will maintain, let's see how we'll handle collision between the edges. Maybe in the future, or maybe in this video itself, we will add a bonus chapter that that shows how to handle collision between points, but it's gonna be in a very similar fashion that the same we're doing the collisions with the screen borders. So let's say we have our screen, which right now it's 1280 x 720 resolution. We have our point, which is moving in some arbitrary direction, and at one frame it moves off the screen. We will catch this using if the X or Y position had moved off the screen. We have access to its old position. Now we need to set it back on the screen as well as send it flying off in the other direction. But it's not that easy because we only have the old position to work with, remember? So we need to modify that old position somehow. What we'll do, first of all, is move the current position to be within the bounds of the screen. So let's say the X position of a point is somewhat greater than 1280. So we will set it back to 1280. Well, we have our current position sorted out, but we still have our old position to fix. Well, we also have access to the difference between the 2 points, or the velocity as we said in the code, yes? So if the position has moved off the X edge of the screen, we will take that X velocity, and as you can say, the equation says the new old X is going to be the current old X. So in this case, it's going to be 1280 plus whatever velocity we had previously. And we will just set the old position X to this, current X plus velocity X, which will move our old position to be in the current position, which will send our point flying off in the other direction as it should. We will do the same step if the point crosses with the y-axis as well, but I'm lazy to animate that, so you just have to use your imagination for that. So if self dot position dot position x, also I let's make screen settings dot py, and we'll just define our stuff here. Width is going to be 1280, height is going to be 720. Let's say gravity is going to be 0. Just cut paste these, and we will just say that from screen settings import everything. We have that. Okay, we are good. And from screen settings import everything, and we'll just say that if the screen position X is less than 0, well, first thing we'll do is set it back to 0, and the next thing is self.old position X is equal to self.position X plus velocity X. Same will do if the position moves out of the width. I guess we can copy that. Copy, paste. We'll set it back on the width, and yeah. Self.position Y is less than 0. Self.position Y equals 0. Self.old position Y equals self.position Y plus velocity Y. Same thing. If self dot position y is more than the height of our screen, we'll set it back on the height. Now this should resolve collisions with the edges of the screen. Let's check that. Okay, this point is boring, so maybe 90, 90. Oh, whoa. Okay. Let me say, I change this to 100. Okay, so we have a bouncing ball, which doesn't seem to be falling down. Don't know why. This should, I guess we can forget about these and just use what we have defined in the point screen settings. Let's just name this as settings. Yes, please. Okay, it fixed it. Nice. Let's say that our friction is 0.5. Why doesn't the point seem to be falling down? What did I screw up? Oh, whoa. I was adding in the old position all that time? That's a no-go. Okay, now it should be behaving correctly. I didn't even realize that. So, just for fun, let's say point, we'll import random, or actually, maybe not. Import a random. We will say we'll make this empty. We will say for dash in range. Let's do 100 points. Random x equal random dot uniform 0 to 1280, 0 and 720. Random y, and we will just say points dot append a point at random x, random y, with old position as random x minus, I don't know, 10, and random y plus 10. Needs to be in brackets. Let's see what this gives us. What's happening? Okay, I just butchered the things here. And this should be yeah, this should be good to go. Yes. So as you can see, we have points bouncing around the screen. Let's bump up the gravity. Let's just say it is 1 pixel. Yeah. Eventually these will settle down in the bottom. Okay. We have implemented points. Now let us implement sticks. So a stick is, so let's also understand what a stick is. So a stick is going to be in a class in our code, which will have references to the 2 points that it is connected to. And it will have a target distance. Kind of draw It will have a target distance that it will try to keep between the 2 points. So if it gets extended too long, it will contract the length of our stick. If it's too shortened, it will expand the length of our stick. So def init return nothing. This will have point 1 and point 2. Self dot point 1 equal point 1, point 2 equal point 2, and we also need a length. Self dot length equals length. Okay. Def update. First of all, def render screen self returns nothing. High game dot draw dot line between first drawn on screen. Let's rename this to surface. Draw it between color white. Start position is self dot point 1 dot position x. Self dot point 1 dot position y. And then same thing for point 2. So let's just say that we also have a sticks array, and I decided that I want to have a stick between points 0, so the first index of the points list, and the second index of the points list. Points 1. Length, let's just say 10. So it should see a stick. Oh. For a stick in sticks, stick.update, stick.render, screen. Let's also quickly define the update function. Otherwise, the compiler is going to complain. Let's see if we see a stick. What did we screw up? Oh. Position. Yes, so there's our stick. Also, let's make this 2. Yeah, there's our stick. So let's see how we are going to update the sticks now. Let's say we have one point right here and the second point here, which is here. Let's say here. And we have a line going between them. We have our stick. So let's say that the stick length is 60. We have set it in code, explicitly set it to be of stick length, of length 60. But the stick is actual length is, let's say 150, for example, 150. So this point right here is 150. 150. This is 150. So how do we resolve these points? They should be somewhere around here. Should be way short. So around here. So what we can do, first of all, is get the difference of the two. So this is gonna be the stick length that we set it to be explicitly in the code minus the actual length. Right now is gonna be 60 minus 150, which, if I'm not wrong, is 90. Yes, it's going to be minus 90. So this difference variable can end up found up negative if the points are farther apart than they're supposed to be when they're connected by a stick, or it's going to be positive when they are closer than they need to be. So we got the difference. Now we need a percentage. What we will use this percentage for, I'll explain in just a bit. Percentage is difference divided by the actual length. Right now, it's going to be minus 90 times, sorry, divided by 150. 150, which is 0.6 minus 0.6. So this gave us our percentage. Now, what will we use this percentage for, you ask? So let's say I know this actual coordinates. If calculated, the distance between them would not amount to 150, but just for explanation, just assume that these are the positions of the point. So we got a percentage, right? So the x is going to be plus equals both the points. So points, um, points x is going to be points x times this percentage, and same with the y. So points y is also going to be times this percentage. So for this point, the x position's 60% is 120. So we'll add that, but since the percentage is negative, that it will actually be minus 200 minus 120. So it's going to be 80. So let's say it moves like this much on the x-axis. So let's just say this is 80. Completely arbitrary information, I know. And 60% of 50 is 30, and 50 minus 30 is 20. So it moves down to by 20 pixels. And this becomes uh, 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 80 and 20. As for this, 100 minus 60 is 40. So this moves by 40 pixels. It also moves by 40 pixels this way. So and ends up somewhere around here. And it will be 40. So now this stick is correct length of 60. Okay, so this was a lot to explain. Let's get back to coding. So on update, so difference x is going to be self dot point 1 minus self dot point 2 position x, and difference y is going to be the same thing, but in y. In the next, we need to calculate the distance between these points. So we'll just use the Pythagoras theorem. We will know the need from math import. Square root of difference multiplied difference squared plus difference y squared. So this gave us the distance. Now, we have the actual length. We need the difference. Yes. So difference is distance minus self dot length. Oh, it's the other way around. So self dot length minus distance. Then we'll need a percentage. Percentage equals difference divided by distance. That gives us a percentage. Then we'll just update it. Self dot point 1 dot position x plus equals self plus equals percentage of this. Same with the y. Oh, same with second point. And then Same with the y. Okay, so there was a fatal mistake in this explanation. We don't actually use the points x and y. We use this differences x and y. So in code, we'll use this difference and apply the percentages on that, and that add that onto the points itself. So uh, offset x. This is more like um the the difference. Sorry, the actual length x and actual length y. So yeah, that was a fatal mistake. I'm so sorry I scuffed up that explanation. But, well, we don't want to do this. We will just use offset x and offset y. And then another thing is that, remember, there are 2 points. So whatever this uh, offset x and this offset y value comes to, we only need to move half of that, because both the points need to come in half the whatever the math says they need to come in by to compensate for the point. Say if one point is pinned, then maybe you can move the other point by the full amount. We'll look at that shortly. But right now, if both the points are free, they need to compensate by moving 50% of whatever the math says they need to move into. So offset x is difference x times percentage, and offset y is difference y times percentage. Also, like I said, we need to only move half the amount, so we are still multiplying by the percentage here, which we obviously should not be doing. I think we swap out these signs. Also, let's just move it here so it's easier to see. Okay, finally we have our stick. Now, one thing I want to do is if pygame.mouse.get pressed, if we are pressing our left mouse button, we will just say points 0 dot position x and points 0 dot position y equals pygame dot mouse dot get pause 0 and 1. So this should let us control the, yep. So as you can see, no matter how much I shake it around, it keeps its original shape. One thing you'll see is that as I spin it, like really spin it, it starts to expand. And this is something that can be fixed with multiple iterations of the update process. So if in the sticks, if you just update it like multiple times a second, you'll get rid of that. Now, one thing I'm going to do is make a square. So I also wanna make a function that returns the distance between the 2 points. So def distance, this will take 0.1, 0.2, this will return a float, and this will just say from math import sqrt, this will just say difference x equals 0.1 dot position x minus Wait, 2. I guess it don't matter because it's always gonna return a positive float. And then difference. Y gonna be the same thing. This will return the absolute value of the square root of difference squared plus difference y squared. So we need to move this up. So um a point at this location, another point like 200 in front of that, 100, 200, 100, and then a point at 200, 100, 200, 100, and then a point at 200, 200. So this makes our 4 points that form a square. So we can just say point 1, 2, 2, and then from the first to the second point, and then from the second to the third point, and then back from the third to the first point, and then I also want to connect the cross beams of that. So 0 to second point, and then the first point to the third point, and I'll just use distance of points 0 2 same thing here 1 3. This should give us a square. How am I getting float division by 0? Okay, because 2 points overlap. I got it. So okay, this should do it. Yes. So I just arranged the points differently. So 100 100. So it's gonna be 100 100, 200 100, 200 200, and 100 200. So we have a nice cross beam. You can play with it. So this is the basic tutorial. Like the crux of this algorithm is done here. I guess the last thing you can do is just implement if a point is pinned or not. So this is going to be a bool and self dot pinned equals pinned, and we'll just say that do all of this only if not self dot pinned. Then do all of this. So if I say that we'll make these all false, and we'll just say the third point is true, and just so we see it. Okay, so we also need to fix the stick script. But first of all, if not self dot pinned, we'll draw it white. Otherwise, else we'll draw it in red. Let's see if that works quickly. Yes. So in the sticks script, I guess we can check if if not self dot point one dot pinned, then do this. if not self dot point one dot pinned. If point one is not pinned, do this. Actually, if we can say if the point one is pinned, you do all this, but just don't divide it by half. Just move it by the full amount. And if point two is pinned, then do this. If not self dot point one pinned and self dot point two dot pinned, then just uh just do all of these, but compensate by half the amount. Okay, what did we mess up? What did we mess up? Oh, not. Okay, there we go. There we go. And let's say that I want to move the third position. Yes. Sorry, second. That would give us a third. So yep. So yes, the basic crux of the video is down here. This is Verlet integration. You can play with it all you like. You can make a cloth. There are so many things you can do to optimize this. You can implement point collision. Point collision, I think, is going to be like exactly similar to this, but you just take the radius. First of all, in the class, you define another parameter called radius, and then you just check if 2 points, the distance between the 2 points are more than their radius. It's less than their radius combined, so you know that they're overlapping, and then you just detect the collisions. Now you can just solve them, which I think is going to be pretty similar to this. Let's see if I can implement this in code. I'll be right back. Okay, so I am back and I did some off-camera coding. So simple changes really. So first of all, I have, let me show the result first of all. So we have our points, but with collision. They can perfectly balance on top of each other. And also, if you didn't notice, I fixed the border collisions a little bit. So it actually the ball's rim now also gets detected. So first of all, in point, I added a new parameter, radius. And then, well, first change is here. So I'm checking if the position x minus the radius is less than 0. And I'm setting it back to 0 plus the radius. So the entirety of the circle is detected, not just the center point. And same with here. So if it's less than 0, I'm subtracting radius and checking it. If it's more than the width or the height, I'm adding the radius and checking it. Same with the y. So this gives us the nice collisions. Then I implemented a collide function. So, and this takes in the points list. So this list right here, we pass in this to the function, and for every other point in the points list, if the other point is ourselves, we continue. We skip this loop of the for loop, and then we calculate the distance. So remember, in this, we need to get the actual length. So we are getting the actual length. We take in distance x, that position dot x minus our position x. The same with distance y, we're getting the distance, and then we're checking that if that distance is less than our radius and that other sphere's radius combined, then we know that we're colliding, because say this circle has a radius of 10, this circle has a radius of 10 as well. If these overlap, their distance is going to be less than their radiuses combined. So this is the way we detect collisions. And then we need to get the difference. Remember, difference is the desired length, the target length, so to say, and the target length is just self dot radius plus the other dot radius. So if the points are like this, we will just set them like this. And this is going to be both the radiuses combined is the absolute minimum distance. You need 2 points to be without them colliding. So that is our target distance. Then we get the percentage difference divided by the actual length, and we have the actual length right here. The difference combined with the target length. We have the target. This is the target length. We get the offsets, and then we just say self.position.x minus for x and y, and for the other plus and plus. And then again we divide it by 2 because we want to compensate it by 50%. This gives us our nice little collisions. And then another thing I did is whenever the right click was pressed, I add a point at the cursor's location. Second of all, let me show you what happens if I don't run this function like multiple times a frame. So you see the points like collapsing in on itself. This will be abundant if there are a lot of points. You see how they're like collapsing into each other? Yeah, like especially these points in the bottom. Like see how they're collapsing. This will be I think more abundant if we just also give our points a width, so it draws it as a hollow. Yes. So if I just spam a bunch of points, you see how even more points. You see how the points below are like squished into one another. This will be more abundant. Also, our frame rate's taking a hit. You see, there are like 2 points combined into one. So that's what happened if we run it only a singular time a frame. So we run this 5 times a frame, and also we update the sticks 5 times a frame. So, as you can see, it maintains the structural integrity, so to say, nicely. And we can see, once we run this 5 times a frame, the points are not collapsing into one another. So right now, the FPS is abysmal. One way you can fix this is by implementing something called partitioning. You can, instead of checking a singular point against every another point, you can divide the space up into chunks or grids, and each cell, so cells like this, chunks like this, and for each point you only check the chunk that it's in and the chunks and the neighboring chunks, and that will reduce the improved performance by a lot. There are a lot of ways to do this. You can check out Quad Tree. There are really good resources for this, by the way. So, Coding Train, Quad Tree. You can implement a quad tree. You can implement a spatial partitioning. So all of this is just to say that there is some data type that resembles chunks or partitions, and they hold references to the particles in them, the points in them. And instead of running this loop, you can just check the neighboring partitions and the partition you're in yourself. Well, this was it. Thanks for watching the tutorial.
She just pulls away, somehow it turns to rain in a heartbeat. Now she's falling like the last leaves of autumn. So cold, and I can't find a way to bring her home. 'Cause my love keeps falling like the last leaves of autumn.